Hi, I'm Storm. Today, I will guide you through creating a simple COVID-19 simulation within my framework, Violet. The modeling technique we'll be using for this simulation is the SIR compartmental model. In this model, the population consists of 3 compartments: susceptible agents, infectious agents, and finally, recovered agents. When a susceptible agent and an infectious agent come into contact, the susceptible agent will have probability of becoming infectious itself. Gradually, these infectious agents will transition to the recovered compartment, where they can no longer contract the virus nor infect other agents. In Vi, we implement these compartments as states, where the agent acts as a state machine, transitioning between states as certain conditions are met. In Python, we represent this state by defining an enumeration. An enumeration allows us to give each state a readable name, while also enabling us to work with these states in a type-safe way in our code. To define an enumeration, we first import the int_enum class from Python's built-in enum module. Next, we create a class called state, which inherits this int_enum class. On this class, we define 3 constants which represent our 3 different states, with each of these constants having a unique number. Now that we've defined the state enumeration, we can start using it in our agent. We will create a new COVID agent class and add a property called state to it. To allow our IDE to provide autocompletion to us, we will specify the type of this property as well. While type hints are very common in other languages, they were only recently introduced to Python, so make sure you have the latest version of Python installed so you can make use of these type hints, as well as the match statement, which we will discuss in a bit. Finally, we must set a default value for our newly added state property. As the majority of our agents start out in the susceptible state, we will set the default to state.susceptible. Note that the virus has to start somewhere, so let's introduce our patient 0. To conditionally set a variable upon an agent's initialization, we can implement the onSpawn function. Here, we check whether the identifier of the agent equals 0 to then assign it the infectious state. To make sure our patient 0 stands out, we also want to change its image index. However, currently we have no images at all yet, so let's implement that first. We will create a new simulation and spawn 1500 instances of our COVID agent class. In addition, we assign 3 images the agent can use: a black, red, and green circle. With the images in place, we can now set the infectious agent's image index to 1 to highlight this agent in red. Finally, we call run on the simulation. When we now execute our script from the terminal, we see a lot of wandering agents in black with exactly 1 agent in red. We're just getting started though. Next up, we will define the conditions under which an agent can transition from one state to the other. As we want to keep the agent's default wandering behavior, we don't touch the agent's change position function. Instead, we implement the update function. Here, we can make use of the match statement, newly introduced in Python 3.10. The match statement allows us to match against the value of self.state, and when this state equals state.susceptible, and the probability of becoming infected is greater than a random value between 0 and 1, the agent transitions its state to state.infectious. In addition, we make sure to change the image index to 1 to match what we implemented in the onSpawn function. To make sure that all arms of our match statement reuse the same random value, we call random.random above the match statement and assign it to a variable. By calling random.random unconditionally, we ensure that the pseudo-random number generator stays deterministic, which is key when running experiments with fixed seeds. As we don't want to execute any code when we cannot make a state transition, we will write an additional case where we can represent the fallback by an underscore. The body of this case exclusively contains the keyword pass, which will instruct Python to break out of the match statement. If we would now try to run our code, it would crash, as we haven't yet defined the infection probability function. So let's do that now. We want to make sure that an agent can only become infectious when it's either close enough to an infectious agent or otherwise spends enough time with 1 or more infectious agents. To implement this behavior, we will use the distance values that are returned by the inProximityAccuracy function. In addition, we check whether the other agent's state is equal to state.infectious. If it is, we increase the probability by the result of subtracting the distance from the proximity radius divided by this proximity radius. This formula ensures that the probability is increased by at most 1, as the infectious agent nears our susceptible agent. When we now run our simulation, we can see how the virus spreads across the population. However, the infectious agents seem to stay infectious forever, which is not what we want. To make them switch to the recovered state after a certain amount of time, we need to keep track of the number of time steps they've been in the infectious state. To do so, we create a new property called counter, which will default to 0. Then, every time the update function is called, we increase this counter by 1. Finally, whenever a state transition occurs, we reset this counter back to 0. With the counter in place, we can now create a function which calculates the recovery probability. To target roughly 5 seconds, we divide the counter value by 300. To make sure the probability isn't skewed by it being pulled every frame of the simulation, we divide the counter again, this time by 60, to act as if the probability is checked roughly once a second. Last, we implement another arm inside our match statement. This time, if the state equals state.infectious and the recovery probability is greater than the random value, the state transitions to state.recovered and the agent's image turns green. With everything now in place, we will run the simulation one more time. Watch how infectious agents slowly transition to the recovered state. Obviously, implementing the recovered state massively reduced the reproduction number. Yet, we have no way of figuring out by how much. Therefore, we will now focus on the data analysis side of this story. I will explain how you can query your simulation's data frame and save extra data to it. Then, I will guide you through some of the more advanced techniques we can utilize to get a better understanding of the data. Last, I will import this data into RStudio, where we'll utilize the ggplot2 library to create some beautiful plots of our simulation's data. Back in our Python script, we slightly change the setup of the simulation. As we want to print its data frame, we wrap everything in a print statement. In addition, we select the snapshots property of the simulation's results, as this holds the data that's collected by all agents. If we now run the simulation for a short amount of time, we see that only a handful of information is available by default. For this tutorial, I've restricted the default column set to just the frame of the simulation in which the data was captured. As the simulation ran for exactly 60 frames, with exactly 1500 agents, the total number of rows equals the number of frames times the number of agents, making up for 90,000 rows. To actually make this data frame useful, let's add some data to it. Back in our update function, we call the saveData function. Here, we specify the name of the column we wish to save to, as well as the data itself. As we want to get some insight into the number of agents that are in each compartment, we save the agent's state property to the data frame. When we now print our data frame, we see the new state column appear. Note that the values in this column are the integer values we defined as part of our state enumeration. Here, the values of 1, 2, and 3 refer to the susceptible, infectious, and recovered states, respectively. Ideally, instead of having one row per agent per frame, we would prefer to have one row per frame, which contains the number of agents belonging to each compartment. To do so, we first import polars, the data frame library that Violet is built on. Next, we want to group our data by the frame column. Combined with the aggregate function, this will allow us to perform all kinds of aggregations, enabling us to merge the data of all agents at each point in time. To count the number of agents in the susceptible state, we write a polars expression. First, we select the column state, and then we filter this column so that it only contains the susceptible state. Note that we don't have to specify the numeric value. Instead, we can simply type state.susceptible, as polars will convert it automatically. To count the number of agents, we call sum, and to name this new column, we call the alias function, where we type susceptible. Finally, we copy the same logic for the other two states. When running our simulation again, we now have access to the total number of agents in each compartment at every point in time. However, our rows aren't chronological anymore. This happens as polars processes our aggregation in parallel, spreading its work across all the cores of our CPU. To make our data frame chronological again, we can call sort and specify that we want to sort by the frame column. Now we can easily check the difference between the number of susceptible, infectious and recovered agents at both the start and end of our short simulation. With the data frame now containing useful data, it's time to make some charts. I'm going to use the ggplot2 package in R. However, you're free to use Python alternatives, such as Seaborn as well. My goal is to make a chart which displays a line for each state, where each line has a different color. For our chart to know which color to draw, we must melt the data frame first. This will transform every row in our data frame into 3 individual rows, where instead of containing all 3 states, they each contain the name of the state and its value. In Polars, we can perform this operation by calling melt, where the frame column once again uniquely identifies our row. In addition, we specify that we want the susceptible, infected and recovered columns to melt into rows instead. Moreover, we instruct Polars to add 2 new columns, a state and an agents column, where state will contain the name of the state and the agents will contain the number of agents. Last but not least, we not only want to print this data frame, but we also want to export it to a file that R can read. Therefore, we assign the data frame to the df variable and both print and export it to Parquet. This file format is relatively new and is similar to CSV. However, it stores data more densely, saving you some precious storage space. When we run our simulation one final time, now for its full duration, we will see how the melting operation transformed our 3 columns into rows. With the data prepared and ready, let's open RStudio. From its console, we will make sure to install the ggplot2 and arrow packages. The former will allow us to plot some fantastic charts, while the latter allows us to read the Parquet file we created earlier. Next, we read the file that we just saved using the readParquet function and assign it to the COVID variable. Then, we call the ggplot function in which we specify the data that we want to use alongside the chart's aesthetics. Here, we specify that we want to plot the frames along the horizontal axis and the number of agents along the vertical axis. Last, we add a line to our chart using geomLine, in which we state that the color of this line should be dependent upon the value in the state column. And that's all there is to it. When we now run our script, we will see a beautiful chart show up on the right, in which the axes are clearly labeled and a legend is provided. In this chart, we can see how the virus reaches a peak right in the middle, after which it will slowly fade away. As a final note, to export this chart, you can call ggsave and specify a file name, so you can include it in a presentation. With our final chart exported, we've had a look at how we can implement a simple COVID-19 simulation in Violet using state machines. In addition, we've explored how we can utilize Polars data frames to dive deep into the data. And finally, we created a simple chart using R's ggplot2 package, so you can easily grasp a full picture of what's going on inside our simulation. I can't wait to see how you push the limits of what's possible in Violet for the weeks ahead. Thanks for watching and happy coding!